Okay, so thank you very much for the invitation. And I will talk mostly about difference equations over elliptic function fields. But as a way of introduction, let me start over the field of rational functions. And maybe I should start by saying a few words about the history. So difference equations, as you know, is a discrete analog of differential equations. And originally, even with Newton, it started with the difference operator x goes to x plus 1, say, and equations or recursion equations with this operator. And then around the beginning of the 20th century, people like Jackson and Adams started considering Birkhoff to Q difference operators. So this is where you substitute for x, qx in the function, and but still over the field of rational functions. And my talk will be about what happens when you consider two such commuting operators. So let me introduce, but eventually over elliptic function fields. But the introduction, I will survey some recent progress over rational functions. And by the way, please stop me, and if you have questions, interrupt me in the middle. So I would like to start with some notation. I take C to be an algebraically closed field. You can think of it as the complex numbers. K is the field of rational functions, and F its completion at 0, the field of Laurent series. And as I said, I consider two Q difference operators, one associated with the number Q, the other one with the number P, complex numbers, non-zero. And I call them phi and psi. Phi f is f of qx and psi f is f of px. And they, of course, commute. And I will denote by s sub phi and similarly s sub psi of f over k, the collection of power series f in f that satisfy a linear homogeneous phi difference equation. So this is exactly like an ordinary differential equation, an ordinary linear differential equation, except that you replace the operator d to the x by the operator phi, and the coefficients are assumed to be, of course, from the field K, rational functions, or if you want, even polynomials. So you consider an equation of the form summation aix f of q to the n minus I x equals 0, and you look for solutions in the large field F. And you let S sub phi be the collection of all such power series. And it is rather easy to see that this is a K subalgebra of F. So the prototypical theorem in this area, or about which I'm going to talk, is this theorem of Besavane-Boutaba from 1922, for which a new proof was given recently by Schäfke and Michael Zinger. And under the assumption that P and Q are multiplicatively independent. So no power of P is a power of Q except for one, of course. Then it is very difficult for a power series in F to simultaneously satisfy a phi difference equation and another psi difference equation. In fact, this happens if and only if this power series is already the expansion of a rational function. So there, in this paper of Schäfke and Zinger, they mention at least 5 more examples of this kind of theorem that concern two commuting shift operators, so the classical difference operators, or two commuting Mahler operators. These are operators where you raise x to the power p and the power q. Of course, p and q are now natural numbers, and to make them automorphisms of the field, you actually have to adjoin all the roots of x to your field, but that's fine. Or you may consider one difference operator, whether a shift q difference operator or a Mahler operator, and one differential operator that commutes with it or essentially commutes with it. So in all these cases, and some of them the theorems were obtained previously. For example, the Mahler case was obtained by Adamczewski and Bell, Jason Bell, proving an open conjecture of van der Kooput. Sorry. Yep. And in all of them, Schäfke and Zinger gave a unified Van der Putten, not Van der Kooput, sorry, my mistake. And all of them, Schäfke and Singer, gave a unified treatment that explained the principles behind these very interesting theorems. And in all the examples, the two operators commuted or essentially commuted. But if you phrase the theorems in terms of difference modules rather than difference equations, and we will come to this. For the moment, I don't want to give the definition of a difference module, but just remember that there is a way to phrase them in a different way, in an equivalent way, but that equivalent formulation renders itself to generalization to the non-commutative case. And in a paper with Jose Gutierrez, we proved recently a similar theorem phrased in terms of gamma difference modules for a couple of operators that do not commute. One is a Q-difference operator, the other one is a Mahler operator, and the group that they generate in the automorphism group of the field is a generalized dihedral group in this case. Now, very recently, in fact, in the last couple of years, Adamczewski, Dreyfus, Hardouin, and Widmer proved two remarkable theorems, or actually more, but I will only cite two, that upgrade these theorems that of Schäfke-Singer type. And for example, in the case of two Q-difference operators, they say the following, that assume that P and Q are multiplicatively independent complex numbers, and F as a formal power series that satisfies a phi difference equation with coefficients from K, then not on, and it is not in K, okay, it is not in the intersection of S phi with S psi, then not only it is not in S psi, not only it cannot satisfy a linear psi difference equation, but actually F psi squared F, and so on are not only linearly independent, but algebraically independent over K. So this is a very significant strengthening. And we say that in such case that F is psi transcendental over K. And the key new tool that allowed them to upgrade the Schäfke-Singer type theorem to this one is the use of difference Galois theory, the analog of Kolchin's differential Galois theory, in particular what's called the psi-parameterized Picard-Vissot theory. And they proved a completely analogous theorem in the case of one Q-difference operator and one derivation, and a few other cases. And as a corollary, you get this strong algebraic independence result that says that if you have now two, not one, power series, that one that satisfies a phi difference equation over K, and the other one that satisfies a psi difference equation over K, but neither of them is in K, then they're algebraically independent over K. Yeah. So this is a survey of this exciting area over the field of rational numbers. So are there questions so far before I go to my own work over the elliptic function fields? Do people hear me?
What is the modules you say before? You mentioned
I will come back to them, the gamma difference modules. I just wanted to inject this notion because it will appear later, and when it will appear, remember that I said that using that formulation rather than the formulation, the classical formulation of equations, you can circumvent the assumption of the two automorphisms commute with each other. Okay, so let us introduce some notation and go over to the elliptic setup. So for any lattice lambda in the complex numbers, I denote by K lambda the field of lambda elliptic functions generated over C by the Weierstrass P function and its derivative. And as in the Mahler case, where we had to take to make the endomorphisms of raising to power P or raising to power Q, to make them automorphisms, we had to adjoin all roots of X. Here we have to adjoin really the elliptic functions on all sublattices of lambda naught. So this is an algebraic way of passing to the universal cover, but I let K be therefore the union of these K lambdas for all the sublattices in a given lambda naught, or if you want, for all the lattices commensurable with a given lattice lambda naught. But this is the small field, the global field. And it sits inside a very large field, F, of all Laurent power series, of course, via the Taylor-Maclaurin expansion at 0. And I take two integers this time because I'm considering the isogenies on the elliptic curve of multiplication by P and multiplication by Q. These are numbers that have now to map the lattice into itself. And I need to assume for my own work, this is something that I would like to relax, but at the moment I need to assume a stronger assumption that they are not, that they're linearly independent, and this is that they're relatively prime. But they need not be prime, but just relatively prime to each other. And I consider the automorphisms of the field K of substituting QZ and PZ for Z in the elliptic function, and I call them as before, phi and psi. And another difference is that we have to introduce now a ring which is larger than the field K, but still you should think of it as a certain small ring of global functions, and it's the ring generated over K in the field F by Z, Z inverse, so Laurent polynomials in Z, and the Weierstrass zeta function, zeta of Z lambda, which is the primitive of the P function, but in itself is not elliptic function, is not lambda periodic. And in fact, this ring does not depend on which lambda you choose. It's easy to see that if you adjoin zeta Z lambda for one lambda, then you adjoin them all. And it's also easy to see that it is invariant under these phi and psi induced from F. And in fact, it is psi simple. It doesn't have any ideal that is invariant under psi. So the two theorems about which I want to talk today are analogs of the theorems that were proven by various people, as I explained before, over the field of rational functions. But as we shall see, they're strikingly different and not simple analogs. So the first theorem says that if you have a power series, a Laurent power series that satisfies simultaneously a phi difference equation and a psi difference equation with elliptic functions as coefficients, the coefficients are from this field K of elliptic functions this time, then this power series should be in the ring S and vice versa, of course. And the second theorem is this upgrading that says that if F satisfies a phi difference equation and is not in S, then not only it is not in S psi, not only it cannot satisfy a linear difference equation for psi, but it is psi transcendental. So the iterates of the automorphism psi on F are algebraically independent, infinitely many algebraically independent quantities over K. So as before, we get as a corollary a nice algebraic independence result for two different power series satisfying respectively a phi difference equation and a psi difference equation. But this is really following the same lines. And before we emphasize the differences between the two cases, the rational and the elliptic, let me make a few remarks. The first one is that, as I said, I should like to relax the assumption that P and Q are relatively prime. I need it only in one lemma, but really the results should hold under the assumption that P and Q are multiplicatively independent. The second remark is that the second theorem, this strengthening as before, as in the case of Adamczewski, Dreyfus, Hardaween, and Wibmer, follows from the first by Galois theoretic techniques. And the Galois theoretic techniques, the strategy is very similar to the strategy that these four authors take in their GEMS paper that's going to appear this year, I think, in the Journal of the European Mathematical Society. So I will not talk about it. Of course, the input and the framework is different, and you have to prove a few more things, but the general approach for upgrading the first theorem to the second is the same. So I would like in the rest of the talk, or in this talk, to concentrate on the first theorem, the one that says that if F is a power series that is both in the collection S phi and in S psi than it is in this ring S. And before we start discussing it, I want to point out the two very basic differences between the elliptic and the rational theory. So over the rational numbers, in a nutshell, the strategy of Schäfke and Singer is the following. You start with F, which is just a formal power series, or if you want a formal germ of an analytic function or a meromorphic function at 0. And it satisfies these two difference equations with global coefficients for the operator phi and the operator psi. So first you prove by estimates on the expansion of F that actually it converges in some epsilon neighborhood. And then you use the functional equation, either the phi or the psi one, it doesn't matter, to extend it meromorphically globally all over, well, depending, all over C or all over the unit disk, depending on the case. Well, in the Q difference case, it's all over C. In other words, up to some natural boundary, which in this case would be at infinity. And then the whole difficulty is somehow to cross the natural boundary and to extend it to infinity too, but you do it. And this eventually tells you that the function f is globally meromorphic everywhere, including at infinity, and therefore it must be rational and you're done. And in the elliptic case, you basically start by doing the same thing. So you have some f that satisfies some difference equation with respect to x goes to q times x, or z goes to q times z, two such difference equations, and you prove that first of all, it converges in some punctured neighborhood of the origin, and then you extend it meromorphically, and then you want to prove that it is actually elliptic, or close to being elliptic, but you discover that you lost any connection with periodicity, with the lattices. They are nowhere in this strategy. And therefore, you have to prove some periodicity theorem. So these issues of periodicity are very serious and rather tricky, and this is the first basic difference. And as you will see, f need not be periodic. So the basic difference, the second basic difference is that this f eventually is not periodic, not even with respect to a sublattice of lambda, but lies in this larger ring S. And this, in retrospect, reflects a deep algebrogeometric issue of existence of non-trivial vector bundles over these elliptic curves, E lambda, C mod lambda. And these vector bundles were classified and studied by Atiyah in 1957, and we were lucky to have his results because actually this is the only case, the only non-trivial curve where you have a complete understanding of vector bundles over it. And in the rational case, this issue of vector bundles does not show up at all because over the multiplicative group or the additive group, where the other difference equations take place, so to speak, there are no non-trivial vector bundles. So please remember these two basic differences, and this is what I would like to highlight in my talk. Any questions? Any? Do people hear me or? Yep.
Yes, we can.
Yeah, okay, good. So now I come to the definition or to this other language of gamma difference modules. So quite generally, if K is a field and gamma is any group acting on K, we will denote by C the invariance and call it the constant field. And a gamma difference module over K is a finite dimensional vector space M over K, equipped with a semi-linear action of gamma. In other words, for any gamma in gamma, you have an operator phi gamma, which is an endomorphism as an abelian group, but it is gamma linear. In other words, phi gamma of AV is gamma A times phi gamma V, not A times phi gamma V, for A in the field and V a vector. And of course, it's a group action. Phi gamma delta is phi gamma composed with phi delta. So I guess if there are number theorists in the audience, they're probably familiar with the notion of F isocrystals. So that's a very important example. That's very important in periodic Hodge theory, number theory. But the concept is a very natural one, and the people coming from the area of differential equations or difference equations usually consider these cases that I gave before, these examples of difference operators, Q difference operators, Mahler operators, and now operators coming from endomorphisms of elliptic curves. So the connection with the setup that we have been discussing is the following, is via this fundamental example. Suppose we are in this situation. Remember, in this definition, the field F doesn't show up. Okay, it's just a notion of a gamma difference module over K, over the global field. But suppose I take now F, a power series in this much larger field, where still gamma X, and the condition, by the way, that P and Q are multiplicatively independent is exactly the condition that gamma is just a free abelian group of rank 2. And I can take the smallest K subspace of F that contains my power series F and is closed under phi and psi. And the fact that F satisfies simultaneously a phi difference equation and a psi difference equation simply translates, is completely equivalent, because phi and psi commute to the assumption that this vector space is finite dimensional over K. This is very easy to see. And this is the key connection between the language of equations and the language of gamma difference modules. And I should just say that in the non-commutative case, where gamma, say, is generally the Hydril group, is in the case where phi was a Q difference operator and psi was a Mahler operator that I considered with Jose Gutierrez, then the assumption that should replace the assumption that F satisfies difference equations is that this module is of finite dimension. So from now on, we use this language of gamma difference modules, and we fix gamma generated by phi and psi as in our example, the elliptic example. So phi and psi are these endomorphisms of multiplication by P, multiplication by Q, where P and Q eventually have to be relatively prime. And I consider quite generally a gamma difference module over this field K. But remember that eventually we want to apply it in this example that comes from our F. But from now on, I will be using the language of gamma difference modules. And as in linear algebra, you want to fix a basis and express everything in terms of coordinates. So, okay, so you can express in the basis of K the operator phi phi and the operator phi psi. You get matrices Aij and Bij as in linear algebra. And except that traditionally it's just a convention. In this case, you call capital A and capital B the inverses of Aij and Bij, but we can live with this. And the condition that phi phi and phi psi commute, instead of being translated to the fact that the matrices commute, the matrices satisfy this consistency condition, or if you want twisted commutativity, that phi of B times A is psi of A times B. And what happens if you change the basis? Instead of having a matrix C that conjugates A and B to A prime and B prime, the transition matrix, as we teach in linear algebra, you have a matrix C that is the matrix that changes the basis that gives you a new basis by what's called twisted conjugation or gauge equivalence in this language of difference equations. So this is all there. Yep.
You're only considering then modules of finite rank, okay?
Always finite dimensional. Absolutely. That's crucial. Yeah. But, you know, that's exactly where you use in this example the assumption that F satisfies both a psi difference equation and a phi difference equation, because you can see that if the if the ranks of the equations are n, the orders of the equations are n and m, then the rank of this m will be at most n times m. Yeah. And as a corollary, by the way, the classification of gamma difference modules over K is completely equivalent to the classifications of consistent pairs A, B up to gauge equivalence, or in the language of non-abelian cohomology, of the determination of H1 gamma GLRK, which is, of course, only a pointed set in general for R bigger than 1. But I want to point it out because this leads immediately to the question of what happens when you replace GLR by other algebraic group G. So in the case of F isocrystals, this was done already in the 90s by Kottwitz in his paper on F isocrystals with G structure. So similarly, there's a whole area here that should be explored of difference equations with G structure that I think is still waiting to be developed. But let us go back and see what we can say about these gamma difference operators. Gamma difference modules. So remember, gamma is this group isomorphic to Z squared, and M is this finite rank gamma difference module over K, but I want to consider it now over F, over the large field of Laurent power series. And then, thanks to the fact that somehow there's only one variable but two operators, Ramis, Loy, and Zhang got a very strong formal structure theorem over this formal field that says that M in such a case must descend to the complex numbers. And by descending to the complex numbers, I mean that there exists, if you want, a gamma difference module over the complex numbers, but because the action on constants of phi and psi is trivial, this is simply a representation of gamma, or if you want, a pair of commuting matrices, of constant commuting matrices, such that M is obtained by semilinear extension of scalars. Okay, so you can take such an M naught and impose on M the phi and psi that take into account the action of phi and psi on F. So this is a very strong assertion that says that in a way M is almost trivial. It's not trivial, but it's as complicated as a pair of commuting constant matrices can be. And the proof is based on the theory of Newton polygons and slopes, and is very similar in a way to the classical work of Dieudonné and Manin in the situation of P-divisible groups, where they studied the same kind of structure theorems for F isocrystals, which is just another example. And it would be very nice or very simple if we could prove the same result over K, not over the completion F. Because then it would follow easily, if the module descended to C, that F belonged to K. And when K is the field of rational functions, this is in fact the strategy of Schäfke and Singer. You start with M, you introduce coordinates, you get a pair of consistent matrices whose entries are rational functions. You know that over Laurent power series, over this huge field F, they are gauge equivalent to a pair of constant matrices. And then you start torturing the gauge equivalence, the matrix that gives you by twisted conjugation this gauge equivalence, and you prove, as I said before, by this method of analytic continuation and overcoming the natural boundary, that you can assume eventually that this matrix is not only in GLR of F, but in GLR of K. So you manage to bring down the gauge equivalence from F to K, and therefore to prove that with respect to a different basis, M as given by constant matrices, in other words, that it is really obtained by extending a representation over the complex numbers. So this is the strategy in all those cases in the paper from 2019 by Schäfke and Singer. But in the elliptic function case, when I started thinking about it, there are surprises. So let us first, to understand what's happening, let us first consider low rank cases. So in the rank 1, still everything is the same as in the rational case. So in the rank 1, let M1 AB be the module of rank 1, K times E, and let phi act by scalars, which, well, I said the convention is that we call them A inverse and B inverse, not A and B, but that's just a convention. And this would be, but A and B are constants, okay? A and B are constants. Then everywhere rank 1 elliptic gamma difference module over K is isomorphic to such an example. In other words, it descends to C, and in fact, in a unique way. And in terms of group cohomology, it simply means that the natural map from C star to K star induces an isomorphism on H1 gamma. But in the rank 2 case, this is already false. And if there's one thing that I want you to remember from this talk, is this pretty example that's very typical, as we'll see, and that's where the zeta function enters. So let zeta be the Weierstrass zeta function, which is either the logarithmic derivative of the Weierstrass sigma function or a primitive of the P function, and now it's a very classical function. And because its derivative is periodic, when you shift the variable by a lattice vector omega, then you get the previous function z of z plus a constant that's traditionally denoted by eta of omega, where eta is this famous Legendre eta function. So all this is 19th or even earlier mathematics. And now let us consider the following functions associated with the natural numbers p and q. GQ is q times zeta minus zeta of qz, all with respect to a given lattice, but it doesn't really matter which lattice you choose in this commensurability class. And GP is the same function with the integer p. And of course, because of this, transformation formula with respect to addition of omega, it's immediate that these two are elliptic functions. So you look at the matrices A and B, which are QGQ01 and PGP01, rank 2 matrices, and you discover that they form a consistent pair. Remember that they said that they satisfy this twisted conjugation. Psi of A times B is phi of B times A. Twisted commutativity equation. So because of that, they define a gamma difference module, which I call M2 standard, which is simply K squared, the two-dimensional vector space, the plane, with phi given by first applying phi to the coordinates, to the two elliptic functions, which are the coordinates, and then multiplying by A inverse, and similarly, the operator associated with psi by first applying psi and then multiplying by B inverse. And the main structure theorem in this rank 2 case will say that every rank 2 gamma difference module, I call it in this case an elliptic PQ difference module, but that's another name for a gamma difference module, either descends uniquely to the complex numbers, either is obtained via semilinear extension of scalars from just an ordinary representation of gamma, rank 2, or is isomorphic to a twist by a rank 1 module of this standard example. Okay, so this starts looking like a nice structure theorem that should tell us something eventually about the problem that we are looking at. So how does the classification of gamma difference modules over K proceed in general? Are there questions so far before I get to the more technical part of the? Okay, I understand people still hear me. I need, yes. I don't see your faces because I only see my slides. So I need to have somebody in the background saying yes or no or something. Yeah. Thanks.
We can hear you.
Okay, good. So hear and see, I hope. Okay, good. So let M be now in general a rank R gamma difference module over this field of elliptic functions over all the lattices lambda. And let's represent it in some basis by a consistent pair A and B. That, remember, it's always only uniquely defined up to a gauge equivalence by some global matrix C. So by the formal structure theorem that I quoted before, we can perform such a gauge equivalence, but with a C that is a matrix in GLR F, not of GLR K, and bring A and B down to a pair of commuting constant matrices. And then an approximation argument tells you that, in fact, you can choose this C to be in GLR of O hat, not just GLR of F. In other words, in GLR of the ring of power series rather than in the field of Laurent series. And then as a result, you also change A and B, of course, in this process. You choose another basis if you want for M, but then as a result, A becomes truly analytic at zero, not only meromorphic. Remember, A and B are globally meromorphic. They're elliptic matrices of elliptic functions. So if they're formally analytic at zero, they're actually truly analytic. And then, as in the rational case, estimates on the formal Taylor expansion of C plus the analyticity of A at zero show you that this matrix C that we use for the gauge equivalence that started its life as a matrix of formal power series is in fact analytic in some open neighborhood of zero. And then you use the functional equation, the equation that A satisfies, you turn it upside down to a functional equation for C. So C valued at Q times Z is AC A0 inverse, and A is globally meromorphic, A0 is even constant. So you see that you can boost up the region of convergence by multiplication by Q or division by Q. And you get that C is everywhere meromorphic, not analytic because A was meromorphic, but everywhere meromorphic on C. But as I indicated before, unfortunately, in this process, we lost all the connection to periodicity, to elliptic functions. You see, you start in just a small disk around zero, and you look at Z goes to Q times Z, so you get larger and larger disks. The coefficients in A are lambda periodic, but how is this going to affect C? Is C going to be periodic? And in fact, it need not be periodic, as in the example with the zeta function that we saw before. So now comes the first main theorem, and this is what I call the periodicity theorem. And to phrase it, I have to use language of sheaves, but only in the classical topology on C. It's nothing sophisticated. So let us denote by O the sheaf of holomorphic functions, complex holomorphic functions on the complex number. And by M, the sheaf of meromorphic functions. And by G, the sheaf GLRM, so it's the sheaf of germs of matrices with entries meromorphic functions. H, similarly, the sheaf GLRO, and F, the quotient sheaf G over H, which is a sheaf of cosets, nothing more. But, you know, cosets have a pointed set, a trivial coset. So what can we say about it? First of all, this matrix C, which is a global matrix of meromorphic functions, remember, it started its life as a matrix in GLR of F, but we managed to show that actually it's a matrix with global, whose entries are globally meromorphic, is a global section of G, of course. F is a sheaf of cosets, but its sections are discretely supported. If you have a section over an open set U, the points where the section is not the trivial coset, the set of points is discrete, has no accumulation point in U. And this is, of course, because zeros and poles of meromorphic functions are isolated. And what are the stalks of F? The stalk at the point psi is GLR of the local field over GLR of the local ring. And this is a well-known object. It's called the affine Grossmanian that comes up in Langland's theory and many other areas in mathematics. Now, there's another structure, and this is that we can translate. We can translate from xi to xi plus omega, say if omega is in the lattice, and therefore we can identify the stalks at xi and xi plus omega, so we can talk in each of these cases about lambda periodic sections. And we denote the space of lambda periodic sections of G, H, or F by gamma sub lambda, and we will be especially interested in gamma sub lambda of F, the lambda periodic section of this sheaf of cosets. And one little more piece of terminology, we call two global sections S and S prime, one a modification at zero of the other, if on the open set, which is the complement of zero, they agree. So they only differ at zero. So now comes the first main theorem. This is the periodicity theorem. And for this, that's where I have to assume that P and Q are in fact relatively prime. So you see, if C, this matrix that we used for the gauge transformation to get to bring down A and B, or the module gamma to a pair of constant matrices, if this was lambda periodic, then we would be done and everything would be easy, as in the case of rational functions. C is not lambda periodic, but the theorem says that you can still salvage something, and what you can salvage is that the image of C in GLR M over GLR O in this sheaf of cosets whose stalks are affine Grassmannians is lambda periodic, well, with a little technical point that you have to allow a modification at zero. So up to changing the value at zero of this discretely supported section, it is lambda periodic. So this is a pretty nice theorem, and to get a better feeling for it, let's see what it says in the case R equals 1, because in this case, F is just GL1M over GL1O, and you know very well that a non-vanishing meromorphic function up to a non-vanishing holomorphic function is simply given by the degree at the point. And so the sheaf is simply the constant sheaf Z via the degree function. And what is CZ? CZ is a globally meromorphic function, one-by-one matrix of meromorphic functions. And if you look back to its role in the gauge equivalence, it says that C is a globally meromorphic function such that C of PZ over C of Z, and also C of QZ over C of Z for relatively prime P and Q are both lambda periodic. And what would be C bar? C bar would be simply its divisor, right? The trace modulo O star modulo, right, of this global section is simply the divisor of it. And in this case, the theorem would say that a suitable modification at zero of the divisor of C becomes lambda periodic. Now, luckily, in the R equals 1 case, we have the Abel-Jacobi theorem, the theory of elliptic functions, and we can infer from this that up to multiplication by some power of C that reflects the need to change things to modify the divisor at zero, and that is really unavoidable, then C is in fact periodic. So in this case, everything is almost as in the case of the rational functions. But as we saw in this example, when the rank was 2, this is not the case in general. So let me now rewrite in another notation what is this space of lambda periodic global sections of F, to which C bar belongs after you modify it by 0. And I call little s the modification by 0 of C bar. So I fixed lattice lambda, and I let A lambda be the adels of the global field K, and O lambda the integral adels. And then it is easy to see that you can identify the global sections of F with GLR of A lambda over GLR of O lambda, or now A lambda is of course a topological ring. And that's where S lies. But remember that C a priori depended on the choice of a basis of M, and you can choose another basis and therefore change C by multiplying on the left by D, which is in GLR of K lambda, of globally elliptic function, globally. So really this S that you get from C by modification at 0 is only well defined as a point in the double coset space GLR of A lambda over GLR of O lambda on the right and divided on the left by GLR of K lambda. And once you see this, you remember that this is a very well-studied object. This is the space called Ban R lambda, or it's actually the set of points of a certain stack, but we don't have to use this high language. And this really classifies, this double coset space, classifies isomorphism classes of vector bundles of rank R on the elliptic curve C over lambda. So to recapitulate, we started with M, we associated to it matrix C that was well defined up to left multiplication by a matrix of elliptic functions, and you modified it 0, you got S, and now we can associate to S a vector bundle E lambda. And because you have these functional equations, or behind the scene, or if you want, because of the structure of this gamma difference module, you get functoriality. You get that if you pull back this vector bundle for one elliptic curve to some unramified cover, you get the same vector bundle for that cover. And that also this vector bundle is in fact invariant up to isomorphism by the pullback by multiplication by P, which is a very strong assumption. And Atiyah classified in 1957 vector bundles and elliptic curves. And among other things, he showed that for each rank R, there exists a unique vector bundle FR, which we would call Atiyah's vector bundle of rank R on the elliptic curve C mod lambda, which is indecomposable. It's not a direct sum of two vector bundles, but it might be reducible. It is reducible, in fact. It has degree 0. In other words, the determinant of this vector bundle is a line bundle of degree 0, and it admits non-trivial global sections. So in rank 1, this would be the trivial vector bundle. In rank 2, for example, the trivial line bundle. In rank 2, this would be the rank 2 vector bundle, which is the unique up to isomorphism non-trivial extension of O by O. Because the genus is 1, such an extension is unique up to isomorphism. And okay, and so given all these functoriality properties with the vector bundles that we associated to our M, we can now prove rather easily the following proposition, that given this M, you can associate to it a unique partition of the rank R into R1 plus R2 plus ... plus RK, such that for all small enough lambda, the vector bundle that we constructed is isomorphic to the direct sum of these indecomposable vector bundles of Atiyah of the corresponding ranks Ri. And furthermore, it is rather easy. I don't know why I couldn't find it in the literature, but it's really just an exercise to write down a representative in this double coset space to the vector bundle of Atiyah. And it's obtained by looking at the following matrix UR. So you take NR to be the nilpotent matrix with ones above the main, right above the main diagonal, and you multiply it by the zeta function of Weierstrass, the Weierstrass zeta function, and you take the exponential, which is, of course, since n is nilpotent, it's a finite power series in zeta, in powers of zeta. And this is UR. And you look at UR, so UR, of course, zeta is not really, strictly speaking, periodic, but the class in the double coset space that it represents is periodic because you mod out by the GLR of O on the right. And this class represents this vector bundle of Atiyah. And that's how the Vasha zeta function comes into the game. So we call store the type of M. And it turns out that if the type is 1, 1, 1, 1, 1, so all these URs corresponding to the FRs are just the trivial matrix 1 of rank 1, then the zeta function does not intervene. And in fact, M descends to C. It meets a C structure. So from now on, for the remaining 5 or 10 minutes, let us assume, to simplify the presentation, that the type of M is R, that we are in the other extreme case where this vector bundle is indecomposable. And in this case, you can perform a gauge transformation, gauge equivalence, to assume that C is UR times D, where D is everywhere holomorphic. And you let T and S be the matrices that you perform this gauge equivalence to A0 and B0 to the constant matrices, and get T and S that are everywhere holomorphic. And then you get this very nice relation that A is UR at QZ times T times UR at Z inverse. And similarly, B, where you take P instead of Q and S instead of T. And there is some tension in these equations because A, is a matrix of globally meromorphic but lambda periodic functions, and T doesn't have the periodicity a priori, but is a matrix of globally holomorphic functions. So for example, if R is 1 and the UR is not there, then simply A equals T forces A by Liouville's theorem to be constant, right? And similarly B. So the key technical lemma is that after conjugating by constant matrix that commutes with UR, that's harmless, this forces T to be very, very simple. In fact, up to multiplication by a scalar A, it's the diagonal matrices with powers of Q, descending powers of Q in the diagonal. And similarly, S with P. And this tells us that in this case where the type is R, and the vector bundle was indecomposable up to a twist by M1AB corresponding to these A's and B's that you see here at the bottom, M is a standard, certain standard module that corresponds to the consistent pair AB given by this equation in the key lemma. And we did it actually. This was the example that I gave you in the rank 2 case. So the final remarks is that the key technical work that I cannot go over is in the periodicity theorem and in this key lemma. And when the type is arbitrary, you get a more complicated structure theorem, but the complication is basically of combinatorial nature. And as we said at the beginning, going back from gamma difference modules to power series satisfying equations, you see that the field F was not there in this structure theorem, but follows by the main structure theorem applied to this example where M is the K submodule generated by the action of phi and psi inside F. So I don't know, I have 2 more slides that I called fun with elliptic functions, just showing you what goes into the proof of the key lemma when R equals 2. So the question is whether I have time for it. Yeah, okay, good. So let me use the last 4 minutes to do what I call fun with elliptic functions, because this is really fun if you like complex analysis. So let us forget about everything and let's just do this little exercise and see what goes on into the proof. So when R is 2, so we need to study the consequences of the following functional equation, say for P, and forgive me, but my convention is a little bit different. Instead of P times Z, I use Z over P, but it's essentially the same. So you have a matrix A that I write little a, b, c, d of lambda elliptic functions, invertible matrix. And you have this zeta, which is, okay, I changed the convention. It's the partial zeta function, but it's P times Q times C. This is my zeta, and I have this matrix U, which is 1 zeta 0, 1. And in higher ranks, it would involve zeta squared over 2 factorial, zeta cubed over 3 factorial, and so on all the diagonals. And you have the matrix T, which is a matrix of globally, an invertible matrix of globally entire functions, everywhere holomorphic functions that they call alpha, beta, gamma, delta. And they satisfy this relation A times U is U at Z over P times T. Now, what can we do with it? Start with the lower left entry. Then you get, multiplying the matrices, that C is gamma. Okay, so C is elliptic, gamma is entire, so they must be, by Liouville, constant. So C and gamma are constants. Go to the right bottom entry and use a bootstrapping argument. Now you know that C equals gamma is constant, and you get the equation C times zeta plus D is delta. Now, zeta is not elliptic, but what you can do, you can sum the residues over a fundamental domain for lambda. And the sum of the residues of delta is, of course, 0, because delta was everywhere entire, no residues. The sum of the residues of D is 0, and because it's elliptic, and the sum of the residues of zeta is 1. And therefore, you get that from summing the residues that C and hence also gamma, which was equal to C, is 0. But now you use this bootstrapping argument, you put C equals 0 into this equation, and now you get the delta equals D, and again, because it's both elliptic and entire, it must be constant. And now you move to the upper left corner, and you can rescale by an easy argument and assume that delta equals D is P, and you get that A is alpha, so it's again constant. And finally, you look at the right upper corner and you get the equation. And now for the first time comes the relation between zeta at Z and zeta at Z over P, that A times zeta of Z plus P is P times zeta at Z over P plus beta. And again, you use this argument of taking residues and the fact that you already know that alpha, which is A, is constant, and you discover by comparing residues that this constant must be 1. But then you substitute 1 instead of A to this equation, and you get that zeta of Z minus P, zeta of Z over P, which is elliptic, is beta of Z minus B, and B is elliptic, you move it to the other side, beta is entire, so you get that beta is both elliptic and holomorphic, so must be constant. And finally, by conjugating by some upper unipotent matrix that commutes with U, you reduce everything and you show that T is 1P and A is this matrix 1GP0P, which after some conventional notation is this example that I gave you before. So you can imagine that in higher rank, things get more complicated because you get powers of zeta. You know, you get zeta to the R over R factorial, and you get this. Things are more complicated, but essentially, these two basic ideas from complex analysis of all the time taking residues, using Cauchy's formula and using Liouville's theorem that allows you, and then making some kind of adjustments and corrections by commuting matrices that allows you to bring your module to this standard form in the case that this vector bundle was really indecomposable. So that is all, and thank you for your attention. And the details of all this can be found in the first reference. The second reference is for the second theorem that's really recent from just last year, and I didn't have time to talk about it. It uses Galois theory and new ideas, Picard-Vissot theory. But as I said in the beginning, in a way, this does follow the strategy in the rational case. So thank you again.